You have a ring whose total charge is Q, let's say, and you have a point P, which is at an axial distance R. In this case, I'm using capital R for the radius and X for the axial distance. All right? Okay, perfect. So this is the point P at which I want to find the field. You want to have a visualization? This is my ring. Okay? Or this is the axis of the ring. The point P is out here. You want a side view? There you go. This is my ring. This is the axis, and axial point P out here, somewhere over here, right? Do you agree that every single point on the periphery of the ring, on the circumference of the ring, is equidistant from the point P? In fact, what is the value of that distance? I'm calling it small r, and that happens to be under root x square plus capital R square. So what's the agenda? I have a uniformly charged ring with charge Q scattered uniformly over the ring at an axial point which is x away from the center. I want to find its electric field. Agreed? Now I'll take an element. Clearly I've taken an element of charge d small q. I will find out the field due to this element. And the field due to this element is dE. There you go, dE. What is this dE equal to? It will be equal to k dq upon r square. Do you agree? But do you understand that when I add all the dEs are actually in different direction, like kind of like arrows coming out of a quiver or like a pencil in a pencil stand. I can't add them like numbers because they are in different direction. So what to the rescue? Resolution to the rescue. Break your dE down into two parts, two components, dEx and dEy. Of course, I have chosen an angle theta. I can very easily make this as angle theta and actually break it down into dE cos theta and dE sin theta in my appropriate directions. Before I go into there, agenda in the previous slide tells us that then we will integrate my dEx and dEy separately. Don't jump to conclusions so easily. How about you monitor the mirror image of this dq charge, which will have its dE out here? Right? Will this dE be equal in magnitude? Absolutely. Will this dE also have two components, dEx and dEy? Agreed. Its dEy will be on the same line and it will cancel the old dEy. All I'm saying is that mirror images, two equal and opposite mirror images on the ring are cancelling their dEy components and retaining their dEx components. In other words, the net electric field, even before finding the value along the axis of the ring, will be along the axis. Axial point field is along the axis itself. That means the only component which is useful is dEx. And dEx is actually k dq by r square cos theta, k dq by r square cos theta, clearly from the triangle. Cos theta is the adjacent upon hypotenuse. Adjacent is x, and you have under root x square plus r square. When you feed the values, guys, you have kx upon x square plus r square to the power 3 by 2 coming out of the integral sign, and what's left inside is a very peaceful dq. What is integration dq? Sum of all charges. What is sum of all charges? Q. And what is the direction of the field? X cap. So E bar is kqx upon x square plus r square 3 by 2 x cap. Don't forget, this Q is the total charge of the ring and it's uniformly distributed. And x cap is actually the axial vector which is along the x-axis or the axis of the ring. If the ring was negatively charged, what happens? Nothing happens except the x cap becomes minus x cap. Even that I don't need to remember. Put the value of charge algebraically. Instead of q, put minus q, you are sorted. Understood?